So my name is Jérôme Harmand, and I work with Ellie at the same lab actually than Ellie at the LBE in Narbonne. And I'm working on the modeling and control of biological systems. And before going a little bit deeper into, let's say, complex models, we thought that it was interesting to go back, let's say, to the basics in terms of what we call dynamical system, dynamical system, and then with an application, specific application to the chemostat. So I apologize in advance if the notions are very basic, but it's important from my viewpoint to have that in mind before going through more complicated models. So I don't know exactly how long time it should take. Probably we will not have time to go at the end of these outline, but we will try to, let's say, have the most important ideas of the most important notions about the dynamical systems. Something I don't know. Do you see the mouse?
Yeah, we see the mouse.
Okay, so I can show you things with it. Okay, thank you very much. So let's go first about let's say the historical little bit history about these dynamical systems. It's not new. I mean, in mathematics, dynamical systems have been introduced for a long time, and even before these dates by Newton, there were a number of work, but the name was not, let's say, used before this date. And within the, let's say, ecology, biotechnology, there are very important, let's say, dates or periods that are characterized notably in the 20th century by some mathematical things that were called strange phenomena. So typically what maybe you have heard about that, but typically systems that are chaotic or systems that are multi-stable. It means that the trajectory oscillates between different steady states, and this was actually new. And from this time, there has been lots of work about using, let's say, the study of simple models in order to study these very strange shaped of trajectories that were not used before. And it has been also discovered because of the emergence of the computers, and then the numerical solutions of dynamical equations, notably because before that time we were able only to solve linear systems and not non-linear systems. So that's why this time is very important. And then in the 80s, basically in the 20th century, sorry, I come back in earlier, there have been lots of work on the modeling, but typically done in very different fields. So in the fields of mathematics, in the field of ecology, and in the field typically of biotechnology, which is interesting here for this class. And what is important to understand is that all these different fields working on modeling have proposed a number of, have used different vocabularies. And in fact, to speak about the same thing, but it has been discovered, let's say 20, 30 years ago only, that many things were completely equivalent, but because they were developed in different fields, they were not known by the others. So in the recent years, lots of work has been done, let's say in the 20 last years, in order to unify the approaches and then understand exactly what we were talking about, population, resource, etc., in different fields. And of course, I just said it, but the computer events and developments change really the things recently. What do we call a model within these lecture? It is really something, let's say, within the family of models you can have in mind. This is a mathematical entity which is deterministic and which allows to formalize the knowledge and then try to understand what happens in what we observe. It can be used to predict something, to control, typically a system. But within you will see that within this lecture, it has nothing to do with comparing a number of, let's say, model simulations with data. What I say is that we can make modeling and work on modeling without any data in mind. So that's very important because that's, let's say, the force of this theory of deterministic differential equations. So that's something very important. Also, keep in mind that a model is, before all, a way of exchanging with people. I mean, try to speak with a biologist, a microbiologist, and ask him what is, or ask her, excuse me, what is a model? And for those people, usually they will answer a model, it depends. And of course, it depends about the conditions, how the things are formalized, how you use them to predict, and so on. So a model for a microbiologist is, for example, a microbe. So it's bacteria, for example, a virus or something. This is a model because it is very well known. In our case, a model is really used to formalize the knowledge. And once you have written a model, then the things are clear. It does not depend on anything else. The model is clear. You speak about this model and that's it. And then you can go forward and see what this model can tell you. In the field of bioprocesses, the models are described by, can be described, and this is the objective of this lecture, so by what we call dynamical systems. A dynamical system is written as a derivative of something which only depends on a number of parameters, probably, and on the state at the instant which is just before. So to know how a state varies over the time, you must know its actual derivative. And that's the way the things are written in this kind of mathematics. This is no less, no more than one equation. So it means that there is a solution or several solutions, maybe. That's it will not be our case in bioprocesses, but it is an equation. And as an equation, it has a number of solutions which can exist or not, which can be studied, as we will see. But what is important to see is that it is a spatial equation. It's not an equation with one single formal solution, but a solution which is a trajectory. So you go from somewhere, which is called initial conditions, and then you go somewhere, which is maybe called steady state if the things are just not moving anymore. So that's exactly what it means. If the system is nonlinear, which is the case in most cases in bioprocesses, then the problem is that we cannot solve explicitly the solution. So it means that we cannot have x of t equal to something. It cannot be solved. It can be solved if the system is linear, but if it's nonlinear, as it will be usually the case, that you cannot solve it. That's a big problem. From a mathematical point of view, it admits a number of conditions for the solutions to exist and to be unique, but I forget these here because, as you will see, we will apply a mass balance modeling to bioprocesses, and let's say there is a kind of rule which says that when you use mass balance modeling, then the solutions exist and they are unique. So that's let's say a mathematical problem that is we just put it out of the scope from here. It is generally represented as a set of differential equations. So x here, x dot equal to f of x and u if we call u the inputs of the system. I will come back on this specific variable. And at the output of the system, then described by y of t equal to g, a function of the state, and eventually some inputs, then this is, let's say, defined as outputs. So this just gives you the notion of inputs, states, and outputs. We define a very important notion is the notion of steady state, what we also call equilibrium points. This is a point called here x bar, which is such that x dot equal to 0. So it means that f of x equal to 0 means that you evaluate f at x bar. And then it allows to study typically the asymptotic behavior of a dynamical system. So it means that you begin by some initial conditions, then the time is going on, the trajectory is computed, and then at some time it goes somewhere. It can be somewhere which is a steady state. It can be, in some specific cases, something oscillating. For example, you have maybe in mind the prey-predator system. There is an equilibrium point, but the solutions oscillate around these equilibrium points. So that's something a little bit special, but usually in bioprocesses, we go towards an equilibrium point which is constant. What do we call a system? It's very important to understand the notion of the concept of system. A system defines what you have in mind when you write a model. This model has a definition in the word. So it means that considering a system, you can define a number of inputs, outputs, and then write down the system under this very general differential form. Typically, you have several kinds of inputs. You have what we call the control inputs that usually are known, maybe not measured, but at least known. For example, you are supposed to fix a given dilution rate, or you are supposed to be able to fix the inputs concentration for your resources, or you are supposed to fix the temperature of your system. It can be an input also, but a number of inputs are unknown. For example, consider you work outside with microalgae, okay, a system outside, and you play with a system where you do not measure the sun, for example, so the radiance. In this case, this is an unknown input. It can be either an unknown input that has nothing to do with your system, but it can be also something which acts directly on your systems. And in some cases, we are able to make the difference between unknown inputs and a given disturbance. What I say is that sometimes some inputs can have an influence of your system and you don't measure them, but sometimes they have an influence of the system and you measure them. So in this case, this is rather a disturbance, but of course you can think of disturbances that are not measured and so on. So it's really a very general viewpoint, but very important because you must be able to define your state of the system, what you want to model, and what comes into the system. And of course, at the, let's say, output of the system, you have a number of outputs that are of interest for you. It can be anything that is defined within your system. In our approaches, these variable will be rather concentrations. So, for example, a number of biomass concentrations, some populations. It can be a number of bacteria, number of virus, or concentration of them. It can be a growth rate. For example, imagine you are interested in estimating a growth rate of something. Then you have your system, and the growth rate in itself can be an output of the system. So you just define the system exactly as you want, depending on what you want to study. Imagine a very simple point of view of an anaerobic digester. It is a system. Of course, you know these kind of physical systems. It is defined as a whole. It means that you have a number of resources, you have a number of biomass. In the simplest way, you have organic matter, you have bacteria, and then they produce, for example, archaeas, and they produce biogas. So in this, let's say, simple way of thinking, you can identify the process in itself with, let's say, the process. Yes, the entity, the here it will be what we call a chemostat, but I will come back on this. So the bioprocess with its volume, what is inside is typically the states you are interested in. So some resources, here a substrate, and some biomass, here written as X. What goes inside this system? You have a flux coming in with an input substrate concentration that I call S in, and with a flow rate that I call Q in. And then at the outside, you have a output flow rate, which is Q out, and you have, if everything here is supposed to be homogeneous, then you have S and X in the output of the system. Now, let's make the mass balance on these. You can compute how the mass here of the resource changes over time. If you consider a little period of time called dt, so, and you make the mass balance, then what has changed is the mass that has entered into the system during dt minus the mass that has left the system during dt, plus something which has possibly be produced minus something that has possibly been consumed. And then you come up with this very general case where you make the mass balance over each of these states. Here, I would like to say that it is written in a very general way. As you see, the volume can vary with time. Something important here about the last equation. You see that the last equation, if Q in is 0 for a long time and Q out is not 0 for a long time, you see that V can become negative because the derivative over the time is continuously decreasing. So it means that when we write these equations, of course, there are a number of conditions. And here, when I write that, in my mind, I must keep in mind that the volume can change between 0 and a maximum of the volume. And this is something which is not explicitly written here, but that you must have in mind when you study such systems. So now, let's go a little bit further, because here you see that we have the derivative of the mass of the resource and the mass of the biomass, but in fact, we want the derivative of the resource and the biomass, not the mass. So how can we do? We use a simple result about the derivative of functions of the two functions which vary with time. And we can simply develop the system. I leave you making this work by yourself, but we can rewrite the things as such and then rearrange everything such that we come up finally with these equations. In these equations, sorry, I have not told you that, but mu is a growth rate, what we call a specific growth rate, and y is simply a yield coefficient. So it means that, say, for example, a cow makes 1 kilogram of meat when it eats, I don't know, 100 kilogram of resources. So that's just what it says here. These are the basic equations for the chemostat. And in a what we call a continuous mode with a Q in equal to Q out, then you see that the last equation becomes 0, simply 0. So the dynamic of V is 0. It does not move anymore. And, oops, sorry. And then you come up with these, let's say, minimal equations of the chemostat. So that's the simple model. These models has a number of properties that we can, let's say, study, sorry. First, notice that this model here can be written without explicitly y in the equations. It is just a change of variable, but you see that a small s is simply capital S is proportional to capital S. So you want to understand the trajectories, how S varies, but you don't really care here about the magnitude of the variation. You just want to understand how it varies with time. Notice that also you can make the sum of ds over dt and dx over dt, and we have what we call an invariance. It means that we have a new variable which is constant, which is a kind of constant. So simply change, try to write down ds over dt plus dx over dt. You will see a number of things disappears, and we can show that this new variable z that I call d here as a dynamic, which is written d s in minus z. What is important here is to understand what I called a little bit before, what I called an equilibrium point. Remember that the equilibrium of dz over dt is such that z bar equal to 0. Okay, so dz over dt equal to 0. So it's z bar such that z bar equal to s in. You see that if z equal to s in, then dz over dt is equal to 0. So what does it mean? It means that when you wait a long time, then z converges towards S in. And this is exactly what we see here. Here, notice that the derivative of dz over dt, the derivative dz over dt is a linear equation. It means that we can write down its solution. And as you see, when the time goes to infinity, the term between parentheses just disappears, and d of t, when t goes to infinity, converts toward S in. So we are able with this model to know that when you wait a little bit, a long time, sorry, then x plus s tend towards S in. This is not surprising because this is simply the mass balance. You forget what we call initial conditions, and then you wait and you converges towards an asymptotic behavior, which is here an equilibrium point. A number of very important things here. You can, let's forget about the normalization, which is just important in terms of concept, but which is not important here for what I would like to say. I would like to say some words about the good practices, good simulation practices. I told you that this model is nonlinear. It means that you must use numerical methods in order to compute the trajectories s of t and x of t from some initial conditions, what I call S0 and x0. Because it is nonlinear, then we can only use numerical systems or numerical solvers that you use, any of them, under Python, MATLAB, Scilab, any computer that you can use. These solvers are usually optimized for variable of the order of magnitude between 10 to the minus 2 and 10 to 2. It means that otherwise we are not really guaranteed to compute correct solutions. So that's very important to have in mind that when you have a complex model, the very important point should be to normalize first the system. Typically, the system like the chemostat should be computed in dividing S by S in, and then you get a new variable, exactly as I showed you before. I made this change of variable, which was a small s equal to capital S divided by y. Okay, so this is another change of variable, which should be important because in this case, S varies between 0 and 1. And then you are really optimal in terms of using your solvers. If you do not do that, sometimes you see in the programs, you see this kind of solution. If x, before computing the derivatives, you see this kind of condition. If x is negative, then x equal to 0. Typically, this should not be done because you are not sure to get the good computer, the good trajectories. Indeed, if your system is well written, x and s should always live in the positive, what we call the positive quadrant. It means that S should not exceed S in and be greater than 0. And for X, this is the same. X should not exceed a maximum and should be positive. Otherwise, it means that you really have a problem. Why some people do that? It's because if you want to get the through solutions, you should, in this case, play with what we call the precision, the accuracy of the solver. But the problem is that increasing the accuracy may increase by hundreds, thousands, the time needed to make simulations. So that's either you increase the precision, either you put these kind of this is tricks, but this is really a dangerous trick because sometimes you don't have the real trajectories computed. So that's something very important. We have a number of systems that are called slow-fast systems. In our case, it may happen, for example, if you work with a resource, for example, a bacteria and a virus. What happens with the dynamic of the virus is that usually their growth is very fast. If you compare the dynamic of the virus with those of the bacteria and of the resource, the dynamic of the virus is maybe 100 faster than the others. What does it mean? It means that you will go 1000 faster to the equilibrium point of the virus. So in this case, you take the equation of the virus, you compute its equilibrium, and you work in the other equations with the equilibrium value of the virus. And you can do that because there is what we call the singular perturbation theory that guarantees that when you do that, it is indeed the asymptotic behavior of the system that in fact you compute. So if you are interested not by the dynamic, but by the asymptotic behavior of the system, first look at the dynamics of the system, and the fast dynamics, change them by the equilibrium and inject the equilibrium value of these variable into the other variables, and then study the other variable equilibrium. So that's what we call the singular perturbation theory. Now, there is also a very, this is a very actually funny thing to do with your simulation, with your simulator. In a number of simulators, remember that's here, okay, you see here the value Q over V. So this is what we call the dilution rate. Q over V is the dilution rate. This is written as D here. Sorry, I probably forgot to tell you that before. It is not the same. Imagine you consider Q over V. Q is equal to 1 and V is equal to 100. And in another case, Q is equal to 100 and V is equal to 10,000. And then make your simulation running. In leaving in the computer the term Q over V. And then you will see that it takes a very long time to the computer to work with 100 over 10,000 instead of 1 over 100, simply because it plays with lots of bits in one case, and the others, it's not, I don't remember, sorry, it's not bits in English, it's, it's you know, the units 0, 1 in numeric. Sorry, I don't remember it in English. It's not important, but simply because the computer has to work with a greater number of 1 and zeros in order to code these large numbers. It takes a long time to compute several times 100 over 10,000 instead of 1 over 100. Even if the ratio is the same. And that's the very important point. So before running simulations, do not forget to optimize your code with these kind of tricks. So for example, here, compute only once and for all the value of D and use D in the equations instead of keeping Q over V. That's very important. So I am sure I will not have time to do everything, but it's not important. Let's go forward and look at a little bit at these. First, what is mu? What is the function mu? Typically, whatever the field in which you look at, which is, let's say, microbiology, biotechnology, ecology, you will have 4 classes of kinetic functions, typically. You will have typically something which is related to the resource dependence, what we call a limitation. I will show you the functions after that. It means that the growth rate is limited by the resource. So it is something like 0 in 0 typically, and then it increases with the quantity, the concentration of resource available in the system. Then, so this is a function which is just increasing, and that can be, probably the mono function, which just arrives at a maximum. So the second function is a problem when there is too much resources. So it means that you are first in the limitation, and then you arrive at the maximum, and then if you go above this one, then the growth rate decreases again. So this is what we call there's a mistake. This is limitation inhibition function. Typically what we call the Andrews or Haldane function. And then there is a very specific kind of kinetic, which is what we call density dependent kinetics. Typically what you may know is the function of Comtois. Comtois has not only the resources as a parameter, but also the biomass. So the biomass inhibits itself. It's very used in systems where an excess of biomass makes that the intra-competition between the bacteria make that it's more and more difficult to access to the substrate. And for the same quantity of substrate, in fact, the growth rate decreases when X increases. So that's something very important. And then there are a number of others, many, actually, in the literature. You have, I don't know, hundreds, thousands of growth rates, specific growth rates. But let's say these are the three first are the main families of growth rate you can see. So when we look at the limitation, there is a very well-known function which is the mono function. Mu max is the maximum. You see that when S becomes very high, it's the denominator is more or less equal to S, and then when S is very high, the growth rate goes to mu max. So this is it is 0 in 0, and it is an increasing function with mu max as an asymptote. It is very interesting to notice that this function was used for many years in different fields. In microbiology, this was proposed by Monod, and then the name of Monod. But this was called the first functional response in ecology for many years. And there is a great paper by Jost, published in 2000, that make a little bit, let's say, a little story of these parallel developments of the two functions. I can provide the paper if if needed. So that's something very important. That's the first, let's say, function we have in mind when speaking about delimitation. It has a number of properties, but I go through because the time is running, and I prefer to go in the other in the other kind of functions. The limitation inhibition function typically is what we call Haldane function. I put some parameters here and just make one simulation to see how it happens. So it is increasing, so it is 0 in 0. It increases until a maximum and then it decreases. What is important, what is, let's say, interesting with this kind of function is that when the parameter ki is very high, so you see that the denominator in this case is exactly as in the mono function. So you can work very, let's say, generally with a lot of genericity with this kind of function, makes this parameter goes to infinity, and then you have the same study that can be done for different functions. So for the substrate, the inhibition by the substrate function, and then come back to the mono function, just playing with one parameter, which is quite interesting for what we want to do. Okay. Okay, I go to the steady state analysis now. And then I will go a little bit fast because I just want you to have in mind the number of results. We can study the steady states, which are which gives you the asymptotic behavior of the system. It means the values towards which your system converges to. You see that I have to solve this set of equations. Remember, this is exactly the dynamic of the system, but given at the equilibrium. So what you can see from the second the second equation is that you have two ways of canceling this equation, either x equal to 0 or either mu of s equal to d. And mu of s equal to d means that you simply have, look, you simply have to plot the function and then plot d, and you see when d crosses the growth rate. So that's what we, I don't care about this. Okay, let's go here. So I plot mu of s and, oh, sorry, I forgot. I come back. Excuse me. I just want to tell you about what is the other steady state. So we have two possible steady states for the system. We have x equal to 0. What does it mean? It means that simply you don't have biomass in your system. So it means that this is a washout solution. Nothing happens, S goes towards S in, and X is simply 0. So it's not, let's say, interesting for us from a practical point of view. So that's why now we are working with the other equilibrium. So of course, there is an equilibrium. The condition for existence is that D is smaller than the maximum growth rate. And then this defines exactly the equilibrium of S that I call lambda of D. Now, if S in is greater than this value, so it means that S can exist, let's say. But imagine that S in is smaller than this equilibrium value. It means that in this case, this functional point with lambda d as equilibrium does not exist because there does not have enough substrate into the system. And then it simply goes to the washout we just said. So there are conditions about the existence of the equilibrium. The washout always exists. Sometimes you go towards it and sometimes you don't go towards it. And the functional equilibrium exists only if D is smaller than mu of S in. I don't want to make the same thing with the limitation with the Haldane function. But the most important point to notice is that at the opposite of what happens with the monofunction, in the case of Haldane function, you have two different possible functional points. And that's something very important in our case. You see that depending on the initial conditions, you can go towards one equilibrium or another one. And that's what we call B stability. I leave you with just these words and I go forwards. I don't go toward these. There are, of course, a number, as in the mono case, there are a number of existence, let's say, conditions. And now I go to something which is important, and I will finish on that, which is the stability analysis of the system. I told you that there are a number of equilibrium points. Actually, we will say that an equilibrium point is stable if you converge towards these equilibrium point. And by definition, if you don't go towards an equilibrium point that exists, it means that it exists, but you will never see it because it is unstable. So you can go towards equilibrium point, which is here represented as a ball in a valley. And you see that if the ball is disturbed a little bit on the right or on the left, it comes back to the equilibrium point. So in this case, we say that it is a stable. Now, what happens if there exist several equilibrium points? Here on the left, you are only one equilibrium point, which is stable. Here in the middle, you have two equilibrium points. You have one equilibrium point, which is stable, and one equilibrium point, which is unstable. It means that if I disturb a little bit this ball, it will go either on the left or on the right. So that's this point is unstable, while this point is stable. Of course, you have you can have many much more complicated situations where you have several equilibrium points, and depending where you begin your simulation, so depending on the initial conditions, you can go into one solution or towards another equilibrium point. So here, depending if you go on the left or on the right, you can go on the left or on the other one of the two stable equilibrium points. So that's exactly what is said here. So let's go. I go toward this. This is just a view, a 3D where you can project, for example, a ball, and then depending where you begin the simulation, it goes in the number of in the valleys, in fact, which are stable, and all the other conditions are unstable, unless you have initial conditions that are exactly on the system, because this is an equilibrium point. So if you begin by exactly the equilibrium point, nothing happens because this is an equilibrium point, the dynamic is zero. So unless you go exactly from there, but if you disturb a little bit, then just you leave the unstable system. Just a remark before concluding. What we call an unstable biological system should be defined when you use this term. Why? Usually, we will speak about an unstable biological system of a bioprocess which goes typically towards the washout. But in terms of dynamical systems, it's interesting to notice that we call an unstable biological system a system which is actually a system which has the washout, which is stable. And this is interesting to notice that when a washout steady state is stable, then we defined a biological system which is unstable. So that's just very interesting to notice from my viewpoint. So this is just a view of the stability and because there are many definitions of stability, but I would like to go. Well, okay, I will finish with these. How do we study the stability of nonlinear systems? In fact, it's actually very difficult to do. What we do, in fact, is that around the equilibrium points that you can characterize, you can compute the points such that dx over dt equal to 0, then this defines your different equilibrium points. Then what you can do is to linearize the system around this equilibrium point. And if you linearize a nonlinear system, you come up with a linear system. And for the linear systems, we exactly know how computing the stability systems. You compute what is called a eigenvalues of the system. This is related, I don't go into details, but when you solve a linear systems, this is a combinations of negative exponential and, of exponentials functions. And you know that if the exponential is negative, you go towards 0, so which is the points around which you have linearized the system is now 0. If the exponential is negative, you go towards 0, so it will be stable, a stable point. And if the exponential is positive, then you will what we call diverge. So it means that you will leave the equilibrium point. So it means that you compute what we call the eigenvalues, and the eigenvalues are precisely the values that you have in the exponential functions that are the solutions of your system, that give you the trajectories of the system. So if these eigenvalues are negative, then the system goes towards 0. It means that this is stable, the equilibrium point is stable, and if you diverge, it is unstable. It's only a numerical approach to compute that. We don't know, or it's very complicated to prove the stability results for nonlinear systems. And I think it's better to stop here. I have a support for this course with the computations, notably of this linearization and the reasoning we can make in order to find these eigenvalues, but it's not necessary to go to these right now, and I prefer to stop here for this first hour of class. Thank you very much for your attention.